Okay, now let's consider the second order condition for the optimality of a convex problem. So suppose we have this function f that is convex, and it's in C2, so that we know we can compute the second order derivative, which is a Hessian of f, and also the Hessian is continuous. Okay, it's in C2. And then we can claim that the function is convex if and only if the Hessian of the matrix at every point is positive, is non-negative definite or positive semi-definite. Okay, so that's the second order. So the second order condition becomes sufficient and necessary for a convex function. Okay, so previously we know that a function is, if we reach to a local minimum, then and the local minimum is an interior point, then we know that this is a positive semi-definite. But now we can say that as long as the function is convex, then this will be always greater than equal to, this will be always positive semi-definite. That means once we reach to a local minimum for this function, we can claim it is automatically a global minimum, okay? Which is really ideal, since we don't need to worry about the local minimum, and every local minimum will be global. Okay, we'll see that soon later. But now let's see why the function is convex if and only if the Hessian is positive semi-definite. So this is actually very intuitive. If you recall, in calculus, when you have a function f that is from R to R, you know that the function is convex if and only if the f of double prime is greater than or equal to 0. And now, since we have multivariate function, then f convex becomes that the Hessian I should write more. The Hessian of f is positive semi-definite. Okay, so this is pretty similar. Just replace this by that. Remember that this one is a matrix right here. So it's positive definite means that for any, if you multiply any vector on the left and right, say I multiply any vector on the left and the same vector on the right, this is always greater than or equal to 0. Okay. All right, so now let's see how to prove this result. Suppose we know the function is convex. We want to show that the Hessian of this matrix, the Hessian of this function at every point is positive semi-definite. To prove this, let's use a proof by contradiction. Assume this is not true. If this is not true, then that means at some point x, this matrix is not positive semi-definite. And that means there exists some vector we call it d, such that when you multiply this d to the two sides of this Hessian matrix at this point x, you get a negative value, you take a negative scalar. Okay? And because this is the case, we know that for this is the continuous function in x, since this one is a continuous, the f is in C2, so the Hessian is continuous in x. And this function is continuous function of x. And that means when you move around a little, around the x, this value is still negative. Okay, since this, as I said, this whole thing can be treated as a function from x to a function from x to a real number. And if you shift x a little bit, it's still a negative value. So that means in the neighborhood of x, we can guarantee this is negative. So what do we mean by neighborhood? If this is the x, we know that near the x, so it is a ball, hyperball, centered at x with the radius small enough, say the radius s, then within this ball, this quantity is always negative, not just at x, but also in the neighborhood. Okay, so this is what we said below. We know that there exists this s radius small enough such that for any for any point in this neighborhood of x, the function this one is negative. So now let's choose a specific one. As I said, this is the x. I have a ball here. The radius I know is the radius here is s. Okay, and now I know the direction d. That makes my value here negative. So let's say that they go along a certain direction. Say this is the d direction. So this originally is the d direction, but I'm going to go along the d direction with this s small enough. So by the way, here we can assume this d to have a unit length. If you like, you can call this d to have unit length, because if you scale this d by some positive number, it's still negative. Right? And then in this case, if you go along the direction d with a step s, so go along from x, go along with the direction d with a step just s, then your y will be in the neighborhood of that, and then the Hessian of y, or every point along this this line will have a Hessian less than 0. Right? So because that, I know that within here, every point has a Hessian, not Hessian less than 0, is every point along in this ball will have this less than 0. So you can replace this x by any point in between. But now I'm just focusing on this this line here. So this f of y is according to the Taylor expansion is equal to f of x plus the first order derivative plus the second order derivative, but it's evaluated at some point in between. So now here, this is the y. Okay, this is the x. And if I just focus on think this as a function of s only, so let's say the phi of s can be defined as f of x plus sd. So I know that when we use another notation by t. So it's f x plus td, and you know that the phi prime of t is equal to gradient f x plus td times d, right? And then the phi double prime t is equal to d transpose gradient, the Hessian of f at this point x plus td times d. That's the second order derivative. Okay, now we can take an expansion. So now phi of s supposed to be the phi naught plus phi prime naught times s plus 1/2 phi prime phi double prime t times s squared, where t is between 0 and s. Right? This is by Taylor's expansion. We know that the last term can have this t, and t is some number that we don't know, but we know where the range is, what the range is. So we know that. Then we can just write it out. This is the f of, according to our definition above, it's just f of x plus s d, and according to our definition of y here, it's just the f of y. Okay, and on the right hand side we have this f of x plus the phi prime at 0. Check this. You just plug in t equals to 0, you will get gradient f of x transpose times d, and there is another s here. So I actually have the d times the scalar s, but d times the scalar s, again, according to that, is equal to y minus x. So that's y minus x. And then equals to 1/2. And then I will have the d transpose. Check this. The d transpose Hessian of f at point x plus td times d, and there is s. So we call that again s is sd equals to y minus x. So I can rewrite this term as y minus x, the Hessian f of x plus t d, then another y minus x. Okay, and that is where this first equation comes from. And now remember that the y is here, and the x plus, so this y is also equal to x plus sd, and t is smaller than s, so that means x plus td is somewhere on this line. But this is in this ball, and if we said that within this ball, this quantity is always negative. So that means this quantity right here will be negative. And this negative means that the whole thing on the right-hand side is less than just the first two terms, since the last term is negative. And that is how we get the second line. Okay? And now from here, you can see that because this f is convex, this cannot happen. Since we know that for convex functions, the f of y is always greater than or equal to f of x plus that. Right? That's from the first previous lecture. So this should be always greater than or equal to that. But now we found some y that such that this is less than that. That is a contradiction to the fact that f is convex. And that is impossible. So that means we cannot really find any x such that any x in the vector d such that this is negative. Okay, now let's look at the other direction. Now suppose we know this Hessian is non-negative everywhere, a positive semi-definite everywhere, and then we want to show that this quantity is true. Okay, this quantity is true. If this is true, then from the previous lecture we know that if f of y is greater than or equal to f of x plus greater than f of x transpose times y minus x for any x and any y, this implies that the f is convex. Actually, this is if and only if, but we require that f to be in C1. Okay, now let's see if we can get the result. Let's again use the first equality. We know this always holds, and because this is a positive semi-definite, then I know this quantity will be greater than or equal to 0, and that implies this second line. Okay, since I have the sum of this term and a non-negative term, so that must be bigger than or equal to the first term. Okay, so we show that for any y, this is bigger than that. Okay, so that implies the other direction. Then we can finish the proof. So this is very important. It's this is a kind of a complement to the previous result. When f is only C1, for f C1, we have to check this condition, but it's not really easy, as you can see. You need to verify this for any x and y. But if also further know the function f is twice differentiable, twice continuously differentiable, means that it's in C2, then you only need to check that. You just need to compute the Hessian and see if it's positive semi-definite everywhere. Okay, so let's see an example. Now we have 3 functions. We just need to, we want to check if they're convex or not. So let's check the first function. So the first function is a univariate function. It has only one variable, x. So in this case, we just need to take the second order derivative and see if it's positive or negative. So we take the derivative twice. You can easily get that it's negative 16. Okay, and note this is negative value, so that means f1 is not convex. So it actually is concave because negative of f is convex. Okay, and this function is pretty clear that this just a function looks like this, negative 8x squared. Okay, so it's concave. For the f2, we have a multivariate function now. It has 3 variables, and it appears to be a quadratic function. As you can see, the highest order is 2. Then we can use the trick we learned before to form this matrix. to form this quadratic function, and it's supposed to be written as the f2 can be written as like a 1/2 q xq x transpose qx plus bx plus c. Right? We can write it in this way. Okay? The question right now is that x is equal to x1, x2, and x3, but what are the q and b? And actually, you know that the b doesn't really matter because we take the derivative twice. The Hessian of f2 will be just equal to q. So we just need to check what this q is. So q, similar as before, we know that we first can write down the matrix A. It indicates the coefficients for the xi, xj terms. So the first one is for x1 squared, that is 4. x2 squared is 3. x3 squared is 5. And we know the x12 has 6, x13 has 1, and there are no other terms, right? So this is 0. And the q will be just equal to half times 1 transpose. Sorry, just q equals to a plus a transpose. The q should be equal to a plus a transpose. And that's just adding this matrix and its transpose. And you can see this becomes 8, 6, 10. This 6 will be added to this 6. This 1 will be added to this 1. And everything else will be 0. And that is this matrix here. And now, since we have the Hessian of the matrix, Hessian of the function, at every point that is equal to this matrix, we just need to check if this matrix is a positive semi-definite or not. And to check the function, to check this, we just need to, there are different ways to check the positive semi-definites of the matrix. One way is to check the eigenvalues. If all the eigenvalues are greater than or equal to 0, then we can claim that. We claim the matrix is positive semi-definite. Or you can just use the original definition. We said that for any vector, say v, you check. This is the matrix that are on the right. We just need to check if this is always greater than or equal to 0 for any v. Okay, and the third way is to check, just for this matrix, to check the leading principal manners. If all of them are greater than or equal to 0, then we can claim, if all of them are greater than 0, we can claim it's positive definite. So the leading principal minors is to check the determinant of this 1 by 1, 2 by 2, and 3 by 3 matrices. Okay, so the first one apparently gives us 8. This gives us, you can check the determinant. It will be just 6 times 8 minus 6 times 6. And that will be 84 minus 36, and that's 12. That means this principal minor is equal to 12. And then you check the last one, and the determinant will be that. So this means that the Hessian is, or this matrix is positive definite. And then according to the theorem above, we know that F2 is convex. And similarly, we can check the F3. So again, it's a quadratic function. And the Q matrix turns out to be this. Okay, now we can check if this one is positive definite or not. Easy ways to check, as we said, that you can check the eigenvalues. It's pretty easy to compute. Just need to take lambda I minus this matrix and check the determinant, right? And sorry, you can check the determinant as you solve for the lambda, and you get two values. One is -4, one is 0, and that means the F3 is negative semi-definite, or negative F3 is positive semi-definite. So in this case, we can claim that the F3 is concave, okay, since it's negative definite, semi-definite. Okay, so the convex function, as we mentioned before, the convex function has a very good property that it doesn't have any local minimum. Every local minimizer is a global minimizer as well. Okay, and this is given by the theorem here. Suppose the function f is convex. Then x is a global minimizer of f if and only if it is a local minimizer of f. Okay, apparently if it's global minimizer, it must be a local minimizer. That's for sure. That's always true. Right? But the point is that if it's just a local minimizer, just the smallest or the minimizer around its neighborhood, can we say that it's also a global minimizer? And this is true for convex functions. Let's see why that is the case. Suppose we have, as we said, necessity is trivial, because if you know this global minimizer, it must be a local minimizer. Now we just consider the other direction. Suppose x is a local minimizer. We want to also show that x is a global minimizer. Okay, since it's local minimizer, I know that within the neighborhood of x, the f of x is the smallest. Okay. In other words, if this is x, then I have a neighborhood of it, and the radius, there must be a neighborhood of x. The radius is r. And within this neighborhood, the f of x takes the minimum function value. So that means any point z in this neighborhood, the f of x is smaller than or equal to f of z, right? So it takes the minimum value at x. Well, you could have other points in this neighborhood that are taking the same value, but no one can take a value smaller than that, okay, since x is a local minimizer. Okay, since this is the case, now let's see if x is not a global minimizer, it's just a local minimizer, but it's not global, meaning that there's another point y that has an even smaller function value of f compared to f of x. So you know that in 1D cases, what this means is, so you have the x, you have the y, right? And you know that x is local minimizer, so it probably look like this, near the neighborhood of x. But if x is not a global minimizer, that means there's some other point that has even smaller function values. For example, there's a y that has value here. Then you know that what you can do, you must somehow bend your curve back to eventually reach the y. Okay, so this is the issue with local minimizer. So we know that you have a function like that. Then there are many local minimizers, like this, but only the middle one is a global minimizer. Others are just locally optimal. Okay, and what we are trying to say here is that if it's convex function, then this case will not happen. Okay, we will not have this case. And to show that, or contradiction, or proof of contradiction, tells us that within the neighborhood, the f of x is minimum, but the f of y is even smaller than f of x. And then what can happen is that if we choose, say, this is the in 1D case. Now, let's say in 2D case, that means in the neighborhood of x, the function value of f of x is the smallest. But the far away, there is a y here, for example, that the value at y is even smaller than value of x. Okay, now I just need to make a connection between the two. Then you can imagine what's going to happen. It's pretty much like this case. If you go along this direction, I know that locally x is smallest, so when I'm still near the x, I know the function value is like that. Okay, but I know that go further along the way to y, the y has even smaller value, so the function value will further decrease. So along this direction, the function value will further decrease. Okay, so that's what happens when I track the function value along this line, and I will get something like that. Okay, and this is how we're going to get a contradiction, because I know the function is convex. I'm going to check that if that's going to happen, or if this happens, then they'll contradict to the fact that f is convex. Okay, and to do that, let's just focus on this line. So I know this is the x, this is the y, and if any middle point, you will know that is even called x alpha, which is kind of convex combination of x and y. So now let's determine the y, the alpha here. I'm going to choose alpha to be that. Okay, so what this means, remember that this is the r. this is the norm of y minus x, or the distance between x and y. So this just the ratio of that. So that means the ratio or the proportion of this over the line here. Okay, if I choose my alpha in this way, then I set my x alpha to be 1 minus alpha x times alpha y, then I know this point right here will be my x alpha. Okay, this will be my x alpha. Okay, you can easily check the fact. So now since this will be my x alpha, and I can also write x alpha in this way. I know that I start from x and I go along this direction with the radius r. So it's this direction here is y minus x divided by the norm of y minus x, because this will normalize the length. So just consider this part. This is the y minus x divided by norm of x. That means the unit vector along this direction. And then I know I go along this unit direction with the radius r. So that's r times this quantity here. It tells me that I'm reaching to the x alpha. So this is another way to interpret how we get this alpha. And now I know that x alpha is in the neighborhood of x, so its function value must be bigger than or equal to f of x. Since x is a local minimum, is optimal near in this circle or in this ball. So on one side, I know, on the one hand, I know this is true. On the other hand, I know that this f of x can be written as 1 minus alpha f of x. So this is equal to that, plus alpha f of x. So I didn't do anything, I just split fx into two parts. One part is a weight 1 is alpha, the other part is with the weight alpha. So now I know that this first term I just copied here, but for the second term, I know that fx is greater than f of y, since y is a global minimizer and x is merely a local minimizer. So I know that this is true. Then I know that this is greater than that. Okay, so now what we end up with is that we found some point along the line between connecting x and y. This point is called x alpha, and found that the function value of x alpha is bigger than the convex combination of the function values at x and y separately. And this is a contradiction to the fact that f is convex, since we know that if you choose x alpha to be such a combination, then the function value is supposed to be smaller than or equal to the convex combination, same convex combination, but on the function value. So, right, and that is a contradiction. And this means that the point x, if it's a local minimizer, it has to be a global minimizer as well. Okay, now there are several simple consequences of that. So for example, if we know the function is convex, then the sublevel set of the function f must be convex. Okay, so the lemma here is to say that the sublevel set of function f is a convex set, and from there we can claim that the set of minimizers of a convex function will also form a convex set. Okay, so starting from this lemma, let's begin with this lemma. So what is a sublevel set? We also know that the level set, here is a sublevel set, means that the set of functions. So we give the c here, you specify the c here. Then the sublevel set of function f is all the points whose function value is lower than or equal to smaller than or equal to c. So from 1D case, this means, for example, I have this is my convex function. This is c. This is the x. This curve is f of x. Then you draw this horizontal line at c. Then this area here is called gamma c. Okay, and you change the c, you see you have a different gamma c. But if the function is convex, then this gamma c will be a convex set. So apparently this is the case for 1D functions. it will not be convex if the function is not convex function. This gamma c will not be a convex set if the function f is not a convex function. For example, if f is like that, okay, and then I draw the c here, then you can see the gamma c is this area and together with this area. Okay, so that gamma c must be non-convex for some c. Okay, in this case, well, if you draw c here, it's still convex set, but if you draw c here, you find a non-convex set. The gamma c will be non-convex. So if the function f is convex, then the sublevel set will be convex for any c. And if it's not convex, means that for some constant c, the gamma c, the sublevel set of gamma c, is non-convex, like in this case. Okay, so the proof is pretty simple. We just need to check that this is the convex set, and by that we just need to show that for any point x and y in this set, the function value, the combination of the convex combination of the 2 points is still in this set. Okay, suppose x and y are in this set, then we need to check if this point is also in the set for any alpha between 0 and 1. And to show that, we just need to show that if this the function value of this point here is also less than or equal to c, right? Because that's how the sublevel set is defined. Okay, to show that is pretty simple. We just evaluate f at this convex combination, and then because f is convex, we know that it must be less than or equal to that. Sorry, less than or equal to that. So this should be f of y. F of y. Okay, this is because of the convexity of f. And then because f, x and y are both in this sublevel set, that means that this is less than or equal to c, and this is less than or equal to c. So the combination of them is less than or equal to c, and that implies the point here is also in the sublevel set, and that shows that the sublevel set is a convex set. Okay, right. So this proves that. So it's convex set or it's empty. So for example, if you choose your C here, it will be empty. But if it's not empty, it must be convex. That's what the lemma says. All right, now the corollary from this is that the set of minimizers form a convex set. So for example, if it's 1D case, then the minimizers of a convex function may look like this. Okay, take the constant value here, and this is the set of points who are global optimizers. Okay, that's 1D case. 2D case or higher dimensional case, you can imagine similar situation. And what we're trying to claim here is that this must be a convex set. And to show that, we just need to realize that if f star is the minimum function value, which is the f star here, then the sublevel set at f star is just this sublevel set at f star is just all the points in omega such that f of x is less than or equal to f star, right? But f star is the minimum value you can get, so it's less than or equal to f star means that it's equal to f of x star. So this is just equal to the set of points which takes the value f star, right? So f star is the minimizer. And this is just the collection of global minimizers, all the points that have taken the minimum value. And this is a convex set, since the f is convex. Okay. Now, so we now consider several. We don't consider the necessary sufficient condition for a global minimizer. Remember that previously, if the function f is not convex, we derived the first order necessary condition and the second order necessary condition for a point to be a local minimizer. But now we show that every local minimizer is global minimizer. So the first order necessary condition, second order necessary, they're not just providing us the candidates, because those points excuse me, because those points will be local minimizer, but any local minimizer is a global minimizer as we showed before. And that means the KKT condition, for example, or the Lagrange condition we derived earlier, they are not just sufficient, but they are also necessary. Meaning that as long as we can find a point who satisfy those conditions, these points will be local minimizer, and at the same time they will be global minimizers since the function is convex. Okay, so this is why the convex functions are so nice in optimization because we can make lots of equivalency relations, or we can provide lots of sufficient necessary conditions for global minimizers. Okay, so to derive that, let's first look at the following lemma. So lemma says that we have a function f that is convex and C1, the gradient exists and is continuous. Then the x star is a global minimizer of f if and only if this is greater than or equal to 0 for any x. So here, this is the gradient at x star, this is the x star, this is the x. Okay, so what this roughly means, you can look at the picture, it's pretty intuitive. Say I have this as my set, say this is my omega. Okay, and it's a convex set since I have a convex function defined over there. Well, if x star is an interior point, for example, if x star is here, then we know that the x star is a local minimizer, or it is also global minimizer since we have a convex function here. So it is a global minimizer if and only if the gradient f of x star is equal to 0, right? And if this is the case, then it doesn't matter which vector you multiply to this vector. Say you multiply this gradient by any vector, since this is 0, so it doesn't matter what you multiply here, it's always equal to 0, right? So that's always true. And what is the significance or difference here is that this also includes the case where the x star is not an interior point. For example, if x star is here rather than in the interior, well, since the x we chose here can be any point from the omega. So the x could be here, or could be here, could be any point in omega. The point is that if the gradient of f at x star is, say it's a vector like that, you basically can imagine that if I have x star like that, and it is taking the minimum function value, then that means my gradient f is supposed to be on this direction. So this vector is showing the gradient f of x star, and this gradient f of x star will have an angle. Say if I draw another over here, this is the x. The angle between the gradient f of x star and this x minus x star will be less than 90 degrees. Okay, so you can see that if you draw any other points, you draw the vector from any other points, you can see that angle is less than 90 degrees because this is a convex set. So when I draw this line, the whole convex set will be on one side. When you reach the minimum here, this shows that y, the inner product of this vector and this vector is greater than or equal to 0, since the angle between them will be always less than or equal to 0. Will be always less than 90 degrees. Okay, so that's the why we have this. So geometrically, it's pretty easy to interpret it. But to prove this, now let's try to prove this. Okay, now let's try to prove this. So to prove this direction, we know that, suppose that x star is global minimizer, and we want to show that this is true for any x in the in omega. Okay, and let's prove it by contradiction. If this is not true, that means there exists some x in omega such that this is less than 0. Okay, that means this is less than 0. And if this is the case, we can define x alpha to be the convex combination of x star and this point that we found. It's a convex combination of the two, and it can be written in another way. It's x star plus alpha x minus x star. So that means I have this x here, or x alpha here, You draw the picture. Say this is a x star, and then I found this x alpha such that the I found this x here such that the x alpha is written as some point in between. So this will be my x alpha. Okay, this is my x alpha. And now because f is in C1, we know that when alpha is small enough, this quantity here will be, this quantity here will be still less than 0. The reason is when x star is really, when we have x alpha prime very close to x star. So that means if this, I'm shifting this point very closer and closer to x star, then this value will go to that, will convert to that, since gradient f is continuous, right? So if I just change the value here, then this value is supposed to be less than 0 as well. Okay, when this alpha prime is pretty close to 0. Okay, and in that case, x alpha is really close to x star. Okay, or x alpha prime is really close to x star. And let's see what happens after then. If this is the case, then we know that at x alpha prime, that means the alpha prime is small enough, it's smaller than certain alpha, and as long as alpha prime is less than certain alpha, that means it is close to x star. So say up to here, this is the alpha. Then everything even closer to x star, it will be alpha prime. Then we can see that the f of x alpha is going to be equal to f of x star plus this. This is like the Taylor's, just to think the same way that we did before. Is we define phi, say phi alpha to be f of x star plus alpha times x minus x star. Okay, so it's a function of alpha only, and x star are given. Then we can check that the phi alpha equals to phi 0 plus phi prime at alpha prime times alpha, where this alpha prime is between 0 and alpha, between 0 and alpha. Right, this is by Taylor's expansion. And then this is the same thing, exactly the same thing as here, as this one, right here. Okay, and now we can see that x alpha minus x star, the x alpha was set to be this. Okay, and this is also equal to this. So I put this x star on the left. Now I only have this left. Okay, I moved x star to the right, and then I only have this left. So this can be shown to be equal to alpha times this. All right. And now because the alpha prime was so close to 0, so x alpha prime will be so close to x star such that this is also negative, and alpha is a positive number, so that's why the second term is totally negative, and that's why this f of x star will be even smaller than f of x star. F of x alpha will be even smaller than f of x star, then that means there will be some point on this line that has even smaller function value than x star. Well, that is impossible because x star is a global minimizer. Okay, so this is where the contradiction comes from, and that means for any x in omega, we must have this less than, we must have this greater than or equal to 0. Okay, for any x in omega, we must have this greater than or equal to 0. Okay. Now, the other direction. Suppose we know this is true. Suppose we know that this is true. This is greater than or equal to 0 for any x in omega. Then we know that first of all, since the function f is convex, I know f of x will be greater than or equal to this. Sorry, it should be plus here, right? We know that if function is convex, then for any function is convex, and f is C1, so this is C1, if and only if f of y greater than or equal to f of x plus gradient f of x transpose y minus x. for any x and y. Okay, now I'm just taking x star to be this x, this x to be this y. Then I will have this equation, this inequality. And because this term is greater than or equal to 0, according to the condition, so this will be further greater than or equal to f of x star, since this is a greater than or equal to 0. All right, and that means that any x in the domain omega, the function value is greater than or equal to the value of x star, and that means x star is global minimizer. Okay, this shows the other direction. Okay, next, let's look at the theorem we were trying to show. Remember that when we were trying to develop the first order necessary condition, we said that if x star is local minimizer, then for any feasible direction d, this is greater than or equal to 0. So this is something I think we learned in the first few lectures in this semester. Okay, and this makes sense because that if you go along the direction, if you start from x star, you know that your x star is a local minimizer, and then that means you go along any feasible direction, the function value can only increase rather than decrease. So that means if you set up any direction, feasible direction d, then you set this x star plus alpha d, f of x star, you set this to be phi alpha. And x star is local minimizer, means that locally phi prime of alpha must be greater than or equal to 0. Sorry, phi prime of 0 must be greater than or equal to 0. And this is equal to the gradient f of x star times dd times d. Okay, and if x star is local minimizer, the d times this fact, d times the gradient will be greater than or equal to 0. So that's a necessary condition that we derived. But since the function f is convex, so we can also show that this is a sufficient condition as well. If we can find a x star such that for any feasible direction at x star, the inner product of these two vectors is greater than or equal to 0, then we can claim the x star is a global minimizer. Okay, so this is not just necessary, but also sufficient. Okay, and to show this, let's first show this direction. Suppose the x star is a global minimizer, then we know that f of x star is less than or equal to any other values, right? Any other function value f at any other points. Okay, and now let's say d is a feasible direction. Then for any, because d is a feasible direction, so we know that from x star, say d is a feasible direction, that means I can go along the direction d for not too far, will be still in omega, right? This means that's the feasible direction. Or in other case, if x star is on the boundary, then d is a feasible direction means that, right? So when alpha is small enough, then we know that we'll be landing up in omega, end up with in omega. So let's say that the we choose this alpha small enough such that the new point we reach up to, say along this direction, I reach to x, and this x is just x star plus alpha d. Okay, started from x star and go along the direction d with step size alpha, and it's still in omega. And then by the lemma above, we know that this will be always greater than or equal to 0. Okay, this will be always greater than or equal to 0. Well, what this one is, because my x star, my x was chosen to be such that this holds, so I can just replace this x minus x star by alpha d. So this is just alpha d. Okay, and then I substitute in, I will get this alpha times that is greater than or equal to 0. Now alpha is greater than 0, meaning that this is greater than or equal to 0. And this shows that this is actually a necessary condition, okay, as we did before. And the key is that how we show that this is also a sufficient condition. How do we show that this is true for any feasible direction d implies that x star is a global minimizer. To show that, let's consider any other point, other point x, we want to show that f of x star is greater than or equal to f of x. Okay, so then for any x, let's set up this x alpha, which is a convex combination of x star and x as we did before. And then we know that the x minus x star, so it's basically the same picture. So I have this x star, this omega, and now x is in here, and the x alpha will be some point in between. Okay, and then the feasible, then the d, which is set to the x minus x star. So this is exactly the vector d, x minus x star. It's vector d. We know that this is a feasible direction because I know I go along this direction. Even up to x, I'm still inside omega. Okay, so d is the feasible direction. And since it's a feasible direction, we know that this is greater than or equal to 0. So this is greater than or equal to 0. But on the other hand, since I chose my d to be x minus x star, so I can replace this d by x minus x star, and that implies this is greater than or equal to 0. And remember, the theorem we had a few pages earlier says that x star is a global minimizer if and only if for any x, this is greater than or equal to 0. Now, for any x, we show that this is indeed greater than or equal to 0, and that means x star is a global minimizer. Okay, a corollary of that is just what we said. If it's an interior point and the gradient f of x star is equal to 0, then not necessarily interior gradient, as long as the gradient f of x star is equal to 0, then we can claim that x star is a global minimizer. Okay, and the reason is you just look at that. If this is equal to 0, then it doesn't matter what direction you multiply, feasible or invisible. We'll just multiply it to this 0, we'll get this equal to 0, which is as greater than or equal to 0. And that means the x star is a global minimizer, right? So just because of this. This is always 0, doesn't matter what the feasible direction d you choose. So this implies that x star is a global minimizer. Okay. Now, in the last few slides, we're going to show that for the constraint case, we specify we'll show that the Lagrange condition or the KKT conditions are actually not just necessary but also sufficient. Okay, meaning that if we have a convex optimization problem, unconstrained or constrained, the Lagrange condition or the KKT condition, especially for the equality constraint convex optimization problem or inequality constraint optimization problems, they are actually also sufficient. Okay, that means that we can only just look at the point that satisfy those conditions, and they will be the only point that are a global minimizer. Okay. So let's start the theorem. I have a function f, and this is C1, and it's convex. And the omega was defined to be the equality constraint set, which is the set of points where hx is equal to 0. Okay, it's the equality constraint. If this is also, so I should say that this gives us a constraint. This gives us a convex set such that omega is convex. Okay, because I have this convex set as the domain of my convex function f, so the set needs to be convex. Okay, so specify the omega is specified by the set of points where h is equal to 0, and this is a convex set. Then we can claim the following: x star is a global minimizer of f over this set omega, if and only if there exists some lambda star. Lambda star is a m-dimensional vector. The m is the same as the codomain of H. See, it's the m here, such that this is equal to 0. Okay, so x star is the global minimizer if and only if we can find this Lagrange multiplier such that the gradient f x star plus this times lambda star is equal to 0. Remember that this first one here is just the one of the KKT conditions, right? One of the Lagrange condition. The other condition is that h of x star is equal to 0. If you still recall, we say that the x star and the lambda star satisfy the KKT condition if this hold, these two hold. Okay, so we already know that x star is in the omega, so we just need to check if there exists some lambda star such that this is equal to 0. Okay, so if it's a global minimizer, then since the Lagrange condition is the necessary condition, so that means this must be true, since it's necessary. The key right now is that if we have this, if we know there exists lambda star such that this is equal to 0, can we show that x star is a global minimizer? Okay, and to show that, let's see that because f is a convex function, so that means for any x in omega, this is true, right? The f of x is greater than or equal to that. So this is the because f is a convex function. Well, on the other hand, we know that this is true for some lambda star. So that means that we can replace the gradient f x star by negative of this. Since I just moved this to the right, I have the negative of that. So the gradient f of x star is just equal to this. And then I can substitute this, since I have the f of x star here. So I just substitute that by this. And then we'll end up with that. Okay, now let's consider any point x in omega. For any point x in omega, we can check that the since x is in omega, so I know any linear convex combination of x star and x is also in omega. Okay, so this point, again, this is the omega, and then this is my, say, x star. This is the x. I know that any point on this line will be in omega, and this point here is x star plus alpha times x minus x star. Okay, because x minus x star is this vector, and alpha times that, alpha is between 0 and 1, means that is somewhere here. Well, this is in omega, but this in omega means that the h evaluates all these points here. When you evaluate h on that, you get 0. So that means h of this is equal to 0. Well, when h of this is equal to 0, we can see that this is equal to 0, this is equal to 0 for any alpha, and this divided by alpha is still 0. So when you take this limit as alpha goes to 0, you will see that this right-hand side will be nothing but the this is the same trick. Let's say we define the psi function to be a function of alpha, that is h of x star plus sorry, don't have this, plus alpha times x minus x star. Okay, and then we know that the psi 0 is just h of x star, and that's equal to 0. But you choose any other alpha, is still equal to 0. Okay, so for any alpha in 0 to 1, and that's why the phi prime at 0, this is a constant function, right? For any alpha. So when you take the derivative, first with respect to alpha, we'll get the d. So I should say, remember that the psi here is a vector value function because it's m-dimensional. Okay, same as h. So this dh x star plus alpha x minus x star times x minus x star. Okay, and then we set alpha to 0, we'll get dh, the Jacobian of h, at x star. Since this alpha, this term will be 0. Since alpha is 0, bx minus x star. Okay, then I know that this must be equal to 0, since this psi actually is a constant function. So derivative must be equal to 0. And that means this is equal to 0. Okay, so that means this is equal to 0. Well, when it is equal to 0, this term is just equal to 0, then the f of x must be greater than or equal to this, since this will be, this side is just equal to f of x star. Okay, and that means x star is a global minimizer. And that finishes the proof.